This is part 2 on drive shafts because there are a lot more topics regarding universal joints that no one can explain. And if you don't get hyperbole, I don't know what to tell you. You should really watch the first video before this one. I don't consider either of these videos true explanations of how universal joints work. Many of my viewers offered great examples of how you understand U-joints to work, and to me there's a difference between observing how something works and be able to explain how it works. I can put a Coke in the fridge, come back later and see that it's cold, but that doesn't mean I can explain how a refrigerator works. That's more of an observation of a result and not really an understanding of the cause. On this channel, we look at the science behind our grown-up toys. My personal requirement to claim I can explain something is to understand the underlying math. I graduated from a difficult engineering school. I took a lot of math. Every engineering class was just another math class. If you've seen my other videos, you know I like to break down the math. For example, in my vertical center of gravity video, I actually derived the math from the ground up. In the piston head video, I explained what influence on oil flow comes from some of the key different terms within the governing equation. When it comes to the equation for universal joint rotation, it's not obvious to me exactly what is taking place. I don't feel like I could derive this equation or explain it with a high degree of confidence, which is why I don't consider this video a true explanation. But I certainly hope you enjoy it and learn something from it. So now I'm going to not explain some more drive shaft concepts, and we all know there are smart people who can explain it better. Let's do a quick review. This is a classic universal joint. It's comprised of a clevis or a yoke. The words are synonyms. And there's a clevis or yoke on both sides. And they're joined in the middle by a spider or a cross journal. This spider has two axes that are coplanar, and each clevis or yoke can rotate about one of those two axes. This is often also called a cardan joint. Cardan is the French word for gimbal, and I guess you could say this center spider is gimbaled in between the two yokes. People will often call this a double cardan joint, and that's just a fancy way of saying two universal joints. You don't hear people say single cardan joint very often, but this is either a universal joint or a cardan joint. Both are correct. Just like clevis or yoke are both correct. Now that we got that nomenclature out of the way, what's important to know is that universal joints are not constant velocity joints. Meaning, if you apply a constant rotational velocity to one half, it doesn't come out the other end as a constant velocity. And the greater the angle, the worse that phenomenon becomes, meaning the faster and slower the output will oscillate. Of course, 1 RPM in has to equal 1 RPM out, but the speed of this rotation can change and does change. It'll go faster, slower, twice each throughout one revolution. And you can see that if you animate this. I've exaggerated this to 70 degrees, so it will be very obvious. This is the input side. Notice how it's rotating at a very constant speed, but the output is non-uniform or irregular. It goes fast, slow, fast, slow. And if you look carefully at this cross spider, you can see how it flip-flops back and forth and how you lose the uniform drive across that plate, and that's what makes the output irregular. So if you have a steering knuckle with a single universal joint, and your crawler has a very sharp steering angle, you will absolutely experience this fast-slow oscillation, which can affect your traction and how smoothly the car drives. Now, if you have a drive shaft with two universal joints, or a double cardan joint, you can unwind or correct that non-uniform rotation. So here you can see we've got both angles set to 70 degrees, and the input shaft is parallel to the output shaft. And you can see the non-uniform rotation of the centerpiece. And because the universal joints are lined up or phased, meaning the axis on each end is parallel, if you have a constant input, it corrects itself and you get a constant output. You can see how smoothly that's turning now. The combination of two universal joints creates a constant velocity assembly. So let's look at another case. Let's say you have two universal joints and they're on the same plane, but the input is not parallel to the output. You've got the same angle on both joints, but they're facing the same direction. If we animate this, it should be very clear. So even though the input and the output are not parallel, you still get a constant input and a constant output because the two joints correct each other. So let's look at another case. Here is a similar double cardan joint or two universal joints, and I've set it up so that the input and the output are no longer parallel. They're skewed. This is actually 20 degrees off of the plane of the input. So we have 70 degrees on both U-joints, but they're askew by 20 degrees. Let's see what happens. Okay, this is the input. It's moving very smoothly. You can see the center shaft is properly phased, meaning the two joints are parallel, but the output is very much non-uniform. So that 20-degree skew has introduced a non-uniform rotation, but we can correct that. So we know that this angle is off by 20 degrees. So what I'm going to do is rotate this clevis 20 degrees from this clevis. So you can see this axis is not parallel to this axis any longer. There's a 20-degree rotation. And that should correct the non-uniform rotation. Let's see if it worked. Okay, so this is the input side. It's rotating constant. And let's flip it around to the output side and check that out. We got that back to constant. So with a prescribed amount of rotation between the intermediate yokes, you can correct that 20-degree skew. You can see the input's constant, and the output as well is now constant. Whereas before we phased these two 20 degrees, this output was very non-uniform. Okay, let's look at another random example. Here we have three universal joints connected, and this first one is at 60 degrees, and then we have a 30 degree and a 30 degree. By having two joints at 30 degrees, you add those together, it equals 60 degrees. That should be the same as a 60 degree and a 60 degree, except we have three joints instead of two. So let's animate this and see what happens. All right, so I've got a 60-degree joint here, 30 and 30. We've got constant input here, but the output, for some reason, is not constant. It's non-uniform. I kind of thought this would work, but it doesn't, and I haven't figured out exactly why, except maybe that there's an odd number of universal joints that they can't cancel each other out. You have to either have 2 or 4 joints to get the full cancellation. It appears as though 230 degrees doesn't equal 160 degrees because this is definitely not a uniform output. If you look at a typical socket universal joint, these are really made inexpensively. You can see that the axis from one end is not on the same plane as the other axis. Instead of having a flat spider, it's got these 2 holes drilled side by side, different locations. So this really creates not only a difference in output velocity, but this is also going to wobble off its axis. And these are really bad for actual automotive drivetrains. They work fine for driving nuts and bolts, but you do want to be careful that you don't use a torque wrench with a universal joint because you won't get an accurate reading. You'll either get slower or faster unless you're perfectly aligned at the exact spot where the velocity is constant across it. Once I had some universal joints at the steering knuckle on my axial SCX24, and they broke very quickly. And you don't see that design very often, but I would certainly avoid this kind of spider design on any RC car application if you happen to see one. Now let's look at another example. Here we've got 1, 2, 3, 4, 5, 6, 7, 8 universal joints, and they're all in the same plane. And I've got 2 facing out, and the rest are facing in. And I've got 1, 2, 3, 4 paired joints, and they're all phased accurately. So at each end of 2 clevises, the axes are parallel. I would consider every single one of these correctly phased. And what do we think is going to happen? My guess is this should be a constant output because everything makes sense. All the angles are the same. You've got even numbers of everything. All the axes are aligned correctly, and everything's on the same plane. So let's animate this and see what happens. This one here is the input. This is what the software is driving. And this is the output. Look at that, it worked. Effectively canceled out all the irregular non-uniform movement and constant in, constant out. Now let's add one more here and just see what happens if we have an odd number of joints together. I got a pretty good idea what's going to happen. And you probably do too at this point. So this is the one that's being driven. This is the input. And let's take a close look at the output. It's subtle, but it's back to non-uniform. Slow, fast, slow, fast, slow. That's because we're one joint away from having it perfectly canceled. This additional joint starts to mess it up again. Now let's take a look at another example. Some of the viewers asked me for this one. It's the same basic layout, only every single paired clevis is now out of phase. You can see that this axle is 90 degrees to this axle, 90 degrees, 90 degrees. Everyone is out of phase. So what is going to happen this time? Any guesses? That's pretty awesome. Every one of these joints magnifies the non-uniformity. So we've got constant input right here, and look how exaggerated this is on the output. It's almost moving at 0, and then it flips almost instantaneously. So we've exaggerated that non-uniformity so many times that it really is pretty funny to watch now. And that's with 8 universal joints in a row. So I built this Lego representation of the CAD model, this same shape, and I've got each of the U-joints phased incorrectly 90 degrees from each other. And let's see what happens. So I can hear it clicking already. That's the input side, which is very smooth. And there's the output side. It's a little difficult to hear the difference between the fast and the slow, so let's take some slow motion footage and see what that looks like. This wasn't perhaps the most precise Lego build. You can see there's some resistance across the entire U-joint drivetrain, and the input is a little bit jerky. And if you look at the U-joints to the left, there's a little bit of hop in them. So there's a little bit of binding, probably because I didn't build this super accurately, but I think you get the point. Look at the output shaft on the right, that gear on the right. Look how it basically just pops its rotation, which is what we would expect. It's got two little hops in it. Again, that's kind of the binding from misalignment along the drivetrain. It's interesting how fast and slow it moves when you've got this many out-of-phase drive shafts in a row. Here is the universal joint equation, which is widely accepted and proven, and I made a plot of one single rotation of a U-joint. So I took the equation and I plotted a bunch of numbers across all different steering angles, or angles of a single U-joint. And this is what the plot looks like. Across the bottom we have one rotation, 0 to 360 degrees. That's one rotation of the wheel, one rotation of the drive shaft. And on this axis here, we have the speed. And the baseline input speed is 10. And that could be 10 RPM, that could be 10 degrees per second. It doesn't really matter, it's just 10. So the input is rotating at 10, and the output is on the y-axis here. And each of these lines is a different steering degree, or angle of one U-joint. Let's just call it steering degree to make it simple. So 10 degrees, your wheels are turned 20, 30, 40, all the way up to 60 degrees. And let's start with this first one, 10 degrees. So if your front wheels are only turned 10 degrees, the variation from the speed of 10 is not very much. But when you get to 60 degrees, look how much it changes. The speed of the output shaft is 20. Remember, 10's the baseline, and it's now 20. That means it's twice as fast at 60 degrees. What's interesting is in the slower direction, at the 2 points in the rotation when it goes slower, it's only going half as slow. Whereas at the fast points, it goes twice as fast, it only goes half as slow. I'm not sure why, but that's pretty interesting. Let's look at a few more lines. Here, we're starting at 50 degrees, and I go all the way up to 90 degrees. The math falls apart at a 90-degree steering angle. So I just put 89.9 to see what would happen. Remember, 10 is the baseline input velocity. And as you turn sharper and sharper, 50, 60, 70, 80 degrees, you can see how much faster it gets. And the red one, 89.9, is completely off the charts. That's because this is approaching infinity in the fast direction. And in the slow direction, it's approaching 0. So that should be a pretty good sign that your U-joint is going to be locked up if you turn it 90 degrees. Now let's look at this a different way that might be easier to understand. Let's look at a percentage change in speed. So the input speed is 0%. That 10 is 0%, that's the baseline. And let's take 60 degrees again. And remember, that was twice as fast, so that's a 100% increase. Now, don't confuse that with 200% of the speed. This is a 100% increase, which is double the speed. So we're going from 10 to 20, that's a 100% increase. And if you're looking at the slower parts, it's going negative 50%, so that's half the input speed. Sometimes percentages are a little easier to understand. They can also be confusing because 200% of the speed is the same as 100% increase in speed. Now, what's interesting is that the fast part is quite short and the slow part is longer. So you've got this short, fast peak followed by a longer, slower section. And again, it's fast, slow for each rotation. So that's 2 pulses, essentially, that your wheel's going to feel for every rotation. Fast, slow, fast, slow. At 360 degrees here, it just returns back to the starting point. Now let's look at one last one. This is the chart that goes all the way up to 89.9%. And as you can see, the red line is completely off the chart. It's way over 200, 500, 1,000. It's infinity % greater. And in the negative direction, it's 100% less, which is going to be a velocity of 0. 100% less is 0. So again, this red line at 90 degrees, your U-joint is completely blocked, both mathematically and physically. All right, who's ready for a brain teaser? Many of you said that you can simply look at a universal joint and understand what's going on. So let's put our brains together and see if we can solve this. Not that you would ever have to solve this in real life. It's a bit of a monstrosity, but it's a fun thought exercise. So it's got an even number of joints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All of the angles are exactly 60 degrees between every joint. And all of the joints are properly phased. Every pair of joints has the axles, what would be considered properly phased. So the first question is, will this output be uniform or non-uniform? If you want, you can pause the video and record your answer before I tell you. So I'll animate it and we can see that the output is definitely non-uniform. You probably could have guessed that. So why is it non-uniform? Where is this discrepancy coming from? Can it be fixed? And if so, how and where would we fix it? Where is this non-uniformity coming from? It's got an even number of joints, they're all phased, and they're all the same angle. So something's up somewhere. So let me know if you think this could be fixed, how it could be fixed, and if there's some degree of phasing we can add to it to smooth it out. Have fun! Stay tuned for part 3, where we will look at some actual crawlers from the internet plus my own setup and break down what's going on. Be sure to subscribe and turn on notifications so you don't miss it.